Space is not silent. Beneath the silence of the void, the universe vibrates with gravitational waves, ripples in space-time, produced by cataclysmic cosmic events. These waves were predicted by Einstein over a century ago, but only recently. Thanks to instruments like LIGO and Virgo, have we been able to hear them. And now, with space-based detectors like LISA on the horizon, the next frontier is opening. The detection of gravitational waves not just from our galaxy, but from galaxies like Triangulum. Imagine this. Two black holes spiral toward each other, locked in a death dance. As they merge, they release more energy in a few seconds than all the stars in the galaxy combined, not as light, but as gravitational waves. These waves stretch and squeeze space-time as they travel, imperceptible to us, but measurable by incredibly sensitive detectors. Triangulum, with its rich population of stars, black holes, neutron stars, and binary systems, is likely a constant source of such signals. In fact, some of the gravitational waves we detect today may have originated millions of light-years away, from within its spiral arms. Even white dwarf binaries, far more common than black hole mergers, produce steady gravitational wave hums that LISA is expected to detect. Scientists are preparing to map the gravitational landscape of the entire universe, identifying the exact locations of binary systems, black hole pairs, and merging neutron stars, including those in Triangulum. These observations will allow astronomers to track the evolution of stellar remnants, measure cosmic distances, and even test fundamental physics. But there's more. The universe has been ringing with gravitational waves since the beginning. Some theories suggest a background hum of these waves has persisted from the early universe, created by inflationary expansion, cosmic string oscillations, or early black hole formations. These primordial waves, combined with those from galaxies like Triangulum, form a gravitational wave background, like the cosmic microwave background, but in space-time. And while individual waves are extremely weak, the cumulative effect across billions of years could subtly shape galactic evolution. For instance, some simulations suggest that gravitational wave radiation might influence the migration of planets in binary star systems, alter asteroid belt structures, or even modify comet cloud dynamics. These effects are tiny, but over cosmic timescales, they might become significant. Imagine entire planetary systems slowly shifting their orbits, not from nearby stars, but from waves rippling through space-time itself. The power of gravitational waves lies not just in their violence, but in their reach. They travel unhindered across the universe, unblocked by gas, dust, or light. They carry information from regions we cannot see, such as the interiors of black holes or the moment of cosmic birth. When we listen to these waves, we are not just hearing collisions, we are hearing history. And the galaxies like Triangulum become orchestras, playing out symphonies of creation and destruction across time. What's even more astonishing is how gravitational waves let us see the invisible. Many black holes and neutron stars are completely dark. They emit no light, no X-rays, nothing detectable by traditional telescopes. But when they merge, they produce a burst of gravitational energy that we can now measure. In that moment, they go from invisible to indelible. Triangulum likely contains hundreds, perhaps thousands, of such hidden binaries, waiting to reveal their presence through these space-time echoes. Over time, this could revolutionize our map of the galaxy, no longer built just from stars and gas, but from ripples and reverberations. In the near future, gravitational wave observatories will be able to detect every white dwarf binary in the Milky Way, track massive black hole mergers across the observable universe, and reconstruct galactic events that left no optical trace. These instruments, orbiting silently in space, will act like space-time microphones, tuned to the faintest tremors of the cosmos. Already, collaborations between gravitational wave data and traditional astronomy have led to multi-messenger discoveries. In 2017, for the first time, scientists detected both gravitational waves and light from the merger of two neutron stars. It was a landmark moment, showing how these waves are complementary to light-based astronomy. In the Triangulum Galaxy, a similar event could happen tomorrow, or it may have happened millions of years ago and its waves are just now reaching us. Every gravitational wave we detect from that distance is a time capsule, a message from the ancient past. And as detection technology improves, we'll uncover not just rare events, but a constant background of galactic activity, the living pulse of the universe. It's fitting, then, that Triangulum, a quiet, unassuming galaxy to the naked eye, may be shouting across the cosmos in a language we've only just learned to hear. A language not of light, but of motion. A language etched in the curvature of space-time. A language that, once deciphered, will rewrite everything we know about how galaxies live, die, and dance.